Hello. Welcome to a short video presentation and overview of the simple manipulator control library. The library used for the control of robotic manipulators. My name is Marko Guberina. I'm a PhD student at Lund University, the Department of Automatic Control, and I am the author of this library and I would like to present and share it with you. This presentation sits within a series of tutorials on the introduction to robotics software. So before this we covered some of the basics of Linux and Python, as this is what's used in the library. And after this presentation there will be more videos that sort of help you get started with the library. So this library is geared towards sort of beginners, novices in robot control, specifically manipulator control. So let's begin. In this presentation, I will give a high-level overview of the library, and because it will be changed quite a bit in the sort of coming months and the years, I will give the future development roadmap so that you know what's you know what to expect going forward. Okay. So this library, well, I'll just start listing off the facts. I prepared the bullets. So this library is written in pure Python, and it runs on Linux. Theoretically, it could run on other systems as well, but this is the only system that it has been tested on. Its primary purpose is to serve as an alternative to ROS. Now you can still use. Okay, so ROS is a software collection of software people use for robotic control, and it tries to do a lot of things. If your particular purpose is to sit down and write a controller for a robotic manipulator, and you want to test it as soon as possible, so your focus is on the control side, maybe on the mechanics side, but primarily the control side, then ROS is a bit of an overkill in the sense that you need to there's a lot of things you need to install, there's a lot of things you need to write, a lot of the APIs you need to respect. And for quick prototyping, this is not really, you waste time if you waste some time if what you're doing is prototyping. And of course, if you're doing things like control, you're primarily prototyping. At some point, of course, you want to develop a full-blown system. At that point, you would have to integrate it with ROS, because there's you need to integrate it with the other parts of the system, like the computer vision and so on. But if you have a relatively simple station, a relatively simple application, then this library is for you. Especially if you're starting off, as a mechanics engineering student that has some. This is fine-tuned for students at Lund University that come to take projects on in robotics with me. And they, but this library can be used for other people as well. That's why I want to sort of explain what's the intended audience for this. So you have some experience with programming, maybe like an introductory course in programming. You know quite a bit of math, all the bachelor level mathematics, and you sort of you're interested in robotics, and there's quite a big hurdle of in the software specifically to getting started on working on robots. That's the best part of robotics, is that you can see things that are moving, and I want to get you there as quickly as possible, especially if you have a keen interest on control as well. This is the part that you find the most fun. I think it's possible that you don't have to spend days, weeks, maybe even months learning ROS, installing it on your system, just so that you can play around a bit with robotic control, get a taste for it basically. Or if you want to prototype as fast as possible, as I mentioned previously. Okay, so again, the intended audience is that you wrote some math on the primary purpose sort of in daily use of this library is you wrote down a controller in math, and you want to get it to run on the robotic arm as quickly as possible. That's my use case as a PhD in robotics. I develop new control algorithms, and I want to get to an experiment as quickly as possible. So if you found yourself in some of this, you have an interest in robotics, you want to get started, or you want to develop very quickly, then I think you want to listen to the rest of this presentation. Okay, so I do have to immediately say that the current status of this is very much in development. I wouldn't even call it an alpha version yet, because if you want to use it right now, it only has a support for the UR5 arm from Universal Robots, and it only does velocity control. But my hope is that I will expand this, and I designed the library in such a way that it can be ported to different robots, and for torque control as well. Now, you don't have to believe me. I'll sort of show the software stack I use to achieve this, and it should be fairly straightforward to get there. It just takes time, as I am the sole developer of this library. Currently, it is shipped with Docker, so you don't have to really do much of anything to get started with using this library for control. The installation is fairly straightforward. There's very few dependencies. There really shouldn't be any problems with getting here. The documentation on the GitLab repository, there's information on how to get started with Docker. And if you're coming to this video from the previous tutorials, there even is a tutorial on Docker, so that you don't, whatever is needed has been covered, apart from the math and the basics of programming within the tutorial series at least. And I really for the library itself as well. There is also documentation for native installation if you want that. Of course, if you're going to work with it a bit longer, it's probably easier to do it that way. And the final point of sort of basic information point I want to give is that there are no real-time guarantees. Okay, at least that there in the future that there might be an expansion for this, depending on if other people join the project. Someone with an expertise in real-time systems. But as it stands, the idea is, you're testing something on the robot, you have your hand hovering above the stop button at all times, because there's no sort of, again, it's for prototyping. And you don't really need real-time guarantees in prototyping if you can stop the robot at all times. If your code runs fast enough, there shouldn't be any problems, at least from my experience. Especially also for programs and control loops that run for up to 5 to 10 minutes or something of this range. It's not really for full autonomy, it's more for the testing of full autonomy. Okay, now let's discuss the technical trade-offs that have been made in the design of this library. Like I mentioned already, you can do all of this, everything that this library offers with ROS, technically. However, there's a certain design choices that are made in this library to make it better for some things than ROS, and of course worse in others. That's classical engineering. We have different trade-offs, and my desire is to get you to use the right tool for the job. If what I've discussed so far is your job, basically. Okay, so how did I gear this library towards mechanical and control engineers and students? The idea was to minimize the code as much as possible, so that you don't have, and make it as have as few of the fancy bells and whistles, so that if you're not an expert with the syntax, you don't have to be. I want to be so little code that anyone who wants to work with this library can simply sit down, read all the code, in an afternoon and be ready. Know everything there is to know, really. And minimizing the code too, I think it's for the core, and with the examples, some of the take one example, take the core, and skip the visualization part. All of this is still less than 2,000 lines of code, so you can really just go at it. And another idea with this, the second way it's optimized for control people, is that the math is directly exposed. This is what I was most frustrated with when I used ROS, because my job is to write down some math and put it, turn that control loop that sits on paper with symbols into an actual piece of code that is the control loop. And what I wanted to see, and it's certainly there. I just had the fact that I even had a difficult time, already sort of proved the necessity for a different piece of software. What I wanted to find was that single line. If you're doing closed loop inverse kinematics, there should be a single line where you take your pseudo inverse Jacobian and you apply it to the error vector, and you get out the vector of joint velocities that you want to command. And then you repeatedly read the state, what the goal is, be it point-to-point motion or trajectory following or whatever, and then you do this one line of computation, and that's it. So really the control loop is the mathematical control loop on paper. There are no other things sort of around it. There are, but it's the minimum wrapper, and this wrapper is non-intrusive in your control loop when you write it down, the actual function. And I'll show all of this in the following videos to make this as easy as possible to use. And then there's the second consideration here. So if you optimize for the speed of the development, you will reduce generalizability and the transferability of this. Now there are ways in which I tried to make this library as transferable to other robots as possible. And in particular, the way this functions is, this library only needs some kind of an interface so a socket interface with any kind of message, with any protocol to read and send them, the message is the protocol that defines them. This library requires this to be implemented in some way, but it only requires the reading of states and the issuing of the control vector to the robot. That's it. So this interface can be incredibly simple. In fact, it might be, and this is very close to my experience, it might be that it's literally easier to write the protocol yourself, starting from a PDF documentation of the robot and the interface it provides, than it is to use some other software to implement this and 100 other things. So how does this work for transferability then? Well, you have this message passing capacity to read states and issue commands, and in the get queue function, for example, get the joint positions, you simply have sort of an if statement where you select, if I'm on this robot, then this is the socket or whatever I'm using to get this vector. If I'm on another system, if I'm simulating, there's something else, and you would simply need to add an if statement for your robot once you've imported this driver or whatever it is that you have. Right now it does really function with if statements, but of course this will be turned into like a class where you specialize this to make it a bit more readable. But again, the point is there's so little code, and it requires so few things, that if you want to port this to a new robot, you can just sit down and write the code. Since you are controlling a robot with the control loop, at least for me, this is possibly you as well, you want to know all the code that's being executed if it's possible, because you want to understand that what the robot will do will be safe for the robot and for yourself. Robots are incredibly expensive. You don't want to break them accidentally. Now, of course, you are simulating things as well, but that's not 100% guarantee. And if you understand the code that's actually being executed, you're much closer to to having the safety as well. And since you already have to do this anyway, you might as well write this few if statements to port to your new robot. Now again, this is my experience. Yours might not be the same. Hopefully, by the time you're watching this, whatever robot you will be working on will already have all of this defined, and the installation instructions for this robot, how to get this driver set up, will be included within this library, at least the text documentation for how to do it. Now you already have some sort of a feeling for how what this library is, what it offers. And you might have noticed so far that I didn't mention not once anything like a computer vision stack or communicating with a different robot and so on. That's because at the current stage I didn't define there is no multi-processing interface to other things. If you just want to have sort of a single camera input, it's very easy to just drop this in to your control loop. Again, I will point you directly in the code for how you would go about doing this, but you would instantiate the process and use the simplest possible kind of messaging, and there is a skeleton for this basically. But this is not enough if you have a full-blown humanoid or like an autonomous tractor or something where you're localizing, you're finding a map, you have to plan a path continuously over and over again. Then at this point you have like 10 different processes, or 20 or 100 or whatever, and it's not feasible for you to actually write a multi-threading operation for all this. At that point you do want to use ROS. Now I will say in the future development it is possible to essentially write the wrappers in ROS control for my library so that you can just integrate with the rest of the ROS system. It's just that this hasn't been done yet, so I'm not advertising it as such. Okay, now let's go a bit again over the current status of the library, what you can expect at what the date today is, the 10th of October 2024. You can expect that it only has a support for UR5E. Now, of course, it has the interface works for all of the UR robots, but I literally just put in only the URDF for UR5, so it's only UR5, and it does take some time to find and ensure that the URDF that you have is correct. This also means that it only works for velocity controlled robots, the commands that I have now. Oh, I should have mentioned in the upper portion for it requires only in this trade-off for speed of development. Once you have the states, the math functions the same way because it's imported. It's mapped to a common class for all robots, so that once you do your Jacobian pseudo inverse or whatever, it doesn't really matter where this vector came from. I just want to explicitly state this. That's how you get the functionality of the library, is that once you have the vectors there, the math functions the same exact way. And this math currently exists only for velocity controlled robots. Now the whole point is that you write your own control loop for whatever control law you have, but there is no need to invent hot water, of course, to spend time with busy work. So there are a collection of basic controllers when you want to, if you have an application that the robot has to go here or there before and after your particular control loop starts. Let's say you want to just develop some polishing, the picking up of the tool, getting to the workspace. You don't want to be hassled by solved problems. So you have things like Movel here. And there's impedance control as well. One example function there is compliant Movel. So on the UR5 arm, there is the force torque sensor here at the wrist. And you can do all these things with impedance control. That works totally fine. The tuning of it works in such a way, I should also say this, immediately with everything in the library is exposed via parameters. So you can vary these predefined functions, you can tune directly by just passing a different argument to your script. And now let's also talk about the future development roadmap, because this is work in progress. It's sort of, well, since I'm the single developer, it's developed according to my needs. So there's no real deadline for any of these things. But I have tasks and plans in the future where I will introduce more to the library that I know that I will need, eventually. So anyway, let's get into this. The number one thing that this will be developed very, very quickly by the end of the year. At the very, very latest, optimal control via the Crocodile library. I'll get into the other libraries I use, but for optimal control, this will be that. And then you'll have the capability to not to have collisions and avoidance with the ARM. This will be programmatically derived, and of course some sort of a table. But anyway, optimal control. There will be some testing at it, because as I add more things, it will. The code will still be quite simple, but it will come to the point where one change could break something else without me knowing immediately what that other thing is, because there will be some auxiliary parts, like in the visualization, for example. So there will be some basic testing, which you can do by just running things in simulation, but it is nice to have it sort of to be able to just execute it programmatically and check that everything works without manually starting all these different simulations and checking for a few things. And this will also include adding some typing, but I'll get to that later. So there will be 2 ports to robots planned within the very near future. The number one is to ABB Yumi, and this will include dual ARM support as well. I have a colleague who works on the ABB Yumi, and he has he's using ROS to control it, and I'm planning to essentially do some through AGM or something like this, get the reading of just the vectors of the states, and issuing a control command that's also just a vector. So this is anyway, I have an idea of how to get this done, and it will be done quite soon. And later on, the library will be extended to support the Franca Amica Panda robot. That means that Franca Amica has velocity inputs as well, but if you have control torque inputs, of course, that's what you want to use. So this will be added as well. Again, there's a very, very clear steps on how to get there. It just requires time, but it's not that it's sort of aspirational. It's more just waiting to become a priority for me. Once the library is ported and to different robots and has torque control inputs and optimal control, so it's sort of like it reached the point where the number of things you get out of the box is considerable. Although again, for its purpose is for people who want to add more things to the robot. That's why it's so simple and so easy to change things. But anyway, at some point, once it gets a bit more mature, it will be rewritten into C++, and the bindings will be provided via PyBind 11. The libraries that it relies on currently are, of course, written in C++, and then they themselves have Python bindings, but it would be nice to have everything sort of to the library as well to follow this paradigm. And I do hope to at that point sort of officially release it in some capacity once this has been done. There's another, like I said previously, there are no real-time guarantees. What I do plan to at least test is to test it with a real-time kernel and possibly add the programs that are being run, at least the main stuff with scheduled deadline. But the real-time kernel will be there, and like there will be the most trivial implementation of this. Not even implementation, usage of the existing tools. And there is real-time in quotation marks, because again, there never will be a guarantee with this library that you can, use it in industrial production and be, sleep tight, knowing that there's zero possibility of anything going wrong. Like I did just hint at before, this code is portable to ROS. I mean, the mathematical computations are very easily, I mean, there's nothing to port there. It's just the inputs and the outputs. And if someone that wasn't me, because I really don't have the time for this, had a time to create the ROS wrappers around the core of the library, then it would comply with ROS control, and it would just work. But that's a bit too much work for me, and this is the reason why this would even exist, is just so that the code that already exists can be integrated with the rest of the ROS ecosystem, and the very nice process management and the priorities. And if at any point this will run on a humanoid, we will need to have these ROS wrappers. This is it. Thank you for your attention. I hope that you will give this a shot if you are sort of within the intended audience that I explicitly outlined. There will be tutorials. There are tutorials again on how to use the library itself. They will include an example of how do you write your own control loop. That will be something relatively simple, but just so that you have a flavor for it. If you are interested in robotics but you don't know enough of Python and Linux, there is in the back catalog of wherever you found this video a list of tutorials, a series of tutorials on both topics, so that you can get up to speed with everything that's being used here. There is context provided in these tutorials, and there are other resources. They're essentially made as a speed run through these topics, just so that you can run something on the robot as fast as possible, but with some context provided, so that you know where to find additional resources if you want to know more. And that's the part you're sort of missing out on. Okay. I hope I piqued your interest. I hope you give it a shot, and thank you for your attention.